if we find out that like the code generate power for
I figured that too. We had and like the very slow down.
Yeah, exactly.
That was
if that is an issue.
the function of switching between.
Well, we have a we made a move, which is pretty much the last picture. I don't think it's very clear.
It is kind of. I know, but
Yeah, that turning there and I have 11 sketches. Most I need to add that one too.
I was going to like. I agree.
I didn't know they do that. I just did. Do you hop in this one?
Okay, good morning everyone. Good morning.
On that one.
All right, couple of quick announcements, which I think you would already seen my email from yesterday. Your exam will be opened up early on Friday morning, around 5 o'clock or 6 o'clock in the morning, okay? And then it will be open all the way until Tuesday midnight. Tuesday, 11:59. Please make sure that you submit your work before the cutoff. Last time, a couple of students submitted their exam a few seconds after cutoff. I did not accept their exams. Please don't let it happen to you. Okay? Tuesday, 11:59 is the cutoff. And even if it is a millisecond beyond 11:59, nothing. All right. Now for the review. And in this class, you fail one exam, you fail the course, so stakes are pretty high. All right. So for the review, we're going to have it over Zoom, unfortunately, because I cannot get a room that will fit all of us within the limitations. Even though not all of us might end up coming, I can't fit it theoretically on paper. So the review will be held via Zoom. And I'll send a link to the Zoom review. This will not be the same as your office hours. They are different. Okay, so please wait for my email. And this review will be on Thursday. At 5:30 p.m. And I'll go from 5:30. I'll stop short at around 6:45 or so. During the review, I plan to solve a problem on fins, and I also want to talk about radiation heat transfer. And what I plan to do between today and hopefully the start of your exam on Friday is I will have a nomenclature of all the terms that you've seen in radiation heat transfer. Okay, so that each and every term is completely defined. If you have any issues, you can always look up that nomenclature sheet, and all of these will be resolved. Okay? All right. So that's about it from my end on these announcements. Are there any questions, please? Yes.
Will the review be recorded?
Absolutely, absolutely. If I'm doing it on Zoom, I mean, even if I were doing it in person, I would have planned on recording using the camera. The review will be recorded. All right, recorded and posted probably Thursday night. Any other questions, please, before we proceed? Okay, exam 2 is similar format as exam 1. You'll have about a couple of questions, subdivisions on each question. You will have approximately 4 hours from the start of the exam to the end. I expect you all, this goes for the entire class, this is getting recorded. I expect you all to uphold the academic honor code. Okay, please do that. Alright. Now we're going to go back to radiative heat transfer. This is the final lap for radiative heat transfer, and this is where everything comes into place, or everything falls apart. So let's look at it. Recap from last time. We looked at what were called as the view factors. Excuse me. Fij, where Fij, and I'm going to write it out, is the fraction of the radiant energy leaving surface I as intercepted by surface J. This is the fraction of radiant energy rate leaving surface I and intercepted by surface J, and we had written this in the following form: Fij was Qij, this is the net rate of radiant heat transfer leaving surface I as intercepted by surface J, divided by the net radiant rate leaving the surface I. Rate of radiant energy from I to J by the total rate of radiant energy leaving surface I. Energy leaving surface I. All right. And then we made use of some expressions from introductory radiative heat transfer. We ended up with two fundamental rules regarding the view factors. These are all obtained from geometry considerations. This is based on geometry. Of surface I and J. So this is purely a geometric thing. Okay, it has nothing to do with the type of surface. Diffuse and gray does not have anything to do with that. And we ended up with two equations. One is called as the reciprocity rule. Fij Ai is equal to Fji Aj. Then we also have the summation rule. Summation J is equal to 1 to n Fij is equal to 1. Please notice the summation is over the index J, not the summation is, it's not over the index I. Okay? And I just want to briefly talk about two examples before we move on. Three surface enclosure, we looked at it last time. Surface 1, surface 2, surface 3. If it is drawn in the following manner, then this tells us that because these are all straight surfaces, whatever radiant energy leaves surface 1 will not be felt back again by surface 1. It will be felt by surfaces 2 and 3 only. So this tells us that F11 is 0, 22 is 0, 330 for the situation that is depicted here. And this also tells us that F12 plus F13 is 1, F23 plus 21 is 1, 32 is equal to 1. Okay, so these are things that you've seen, and if you know one, you know all of them. Consider another example. This is once again a simple one. Let's say that I have surface 1, which is a flat plate. Then I have surface 2, which is this cylindrical or semi-cylindrical enclosure. We're going to solve a problem of this nature today. Surface 2 is the semi-cylindrical enclosure. Then, if I look at surface 1, it should be true that F11 is 0. Does this make sense to everybody? All the radiation that is leaving surface 1 as felt by surface 1 is 0, because surface 1 will not feel any of the radiation leaving it. Which means if I use the summation rule, which tells me that F12 is actually equal to 1, which means that all the radiation leaving 1 will be felt by surface 2. All the radiation leaving surface 1 felt by surface 2. From 1 falls on 2. And F11 being 0 implies that all the radiation leaving surface 1, none of it falls on surface 1. Now I use the reciprocity relationship, or let me go ahead and say, okay, F12, A1 is F21, A2. This is the reciprocity relationship, so that I can calculate F21. Obviously, the surface area of A2 is going to be larger than that of 1. Right, this is circular, that's flat. So this tells me that F21 is less than 1. Which further tells me that if I use the summation rule for surface 2, F22 is actually not equal to 0. So there is a possibility that radiant energy that starts from here will actually, a portion of it fall on surface 2 itself, because of the nature of the surface. Okay? So this tells us that it is not always true that F11, F22 and F33 are 0. There are surfaces for which this need not be 0. Okay? So this tells us that that's the case. And that's the case. So just a representative example. We're going to look at more problems with actual numbers and so on, but we are not there yet. Alright, so we started off with this idea. And what we want to do is, okay, there are all these equations that are seen in radiative heat transfer. So we would like to make use of an analogy between resistive networks and radiative heat transfer, so that it in some ways simplifies the process of solving the problem. Okay, so it is a very elegant method, this resistive network method for radiation, and you will see that it is not the same as the resistance networks that we use for conduction and convection, and for some reasons that we will describe here. So radiative, resistive, or resistance networks. And I started this discussion last time. I'm going to very briefly go over it again, okay, just for the sake of having everybody on the same page. Let's say that I have a 3-surface enclosure. Not necessary, but let's say. And let's say that it is in the following form, so that this is surface 1, surface 2, surface 3. We're going to assume that all of these are diffuse and gray surfaces. assuming that their spectral emissivity is the same as their spectral absorptivity. Gray and diffuse implies that their absorptivity and emissivity are the same. So this implies that epsilon I is equal to alpha I. This is the total emissivity, this is the total absorptivity, they are both the same. And I goes from 1, 2 and 3. Okay, so this is true for all these three surfaces. There are temperatures T1, T2 and T3. We would like to set up a radiative resistance network for this set of surfaces. They are exchanging energy between each other. Of course, we can work with the equations, but not very tractable. So we start off by looking at surface 1. I'm going to define Q1 as the net radiative rate of heat transfer from surface 1. So Q1 is the net rate of radiative heat transfer from surface 1, and as you know, this is in the units of watts. Okay, this is radiative power from surface 1. I'm not particularly saying this is going to surface 2, this is going to surface 3. That's a part of the game. We need to figure out how much is going to 2, how much is going to 3. Okay, so we say, okay, from basic equations, Q1 is the surface area A1 times the emissive flux minus, right, this is the net flux, net radiative heat transfer is emissive flux minus, I have some irradiation on surface 1. If I subtract the 2, multiply with the area, so A1 times alpha 1 G1. This is the expression that we have seen at the beginning of the semester itself. Alpha 1 is the same as epsilon 1, so I can say that Q1 is A1 times E1 minus epsilon 1 G1. This is equation 1. Last class we defined a radiosity. Radiosity from surface 1 all the way to the surroundings. This is the net radiative flux that leaves surface 1, which means this is going to have a part of it through emissive things happening on surface 1. And there is also going to be radiation falling on surface 1, but some of it is going to get reflected. So that's also leaving surface 1. So this is going to be E1 plus the reflectivity times G1. And we looked at this equation last time. Rho 1 is reflectivity. Rho I, typically for our surfaces, they are also opaque surfaces. So opaque plus diffuse and gray. Okay, that's a very strong word, diffuse and gray. Then rho I is the same as 1 minus alpha I, which is the same as 1 minus epsilon I, because it is diffuse and gray. So if I do that substitution there, I get J1 is E1 plus 1 minus epsilon 1 G. I write G1 in terms of J1. We did this last time, I'm just repeating the steps. G1 is J1 minus E1 by 1 minus epsilon 1. There is no indication that these are all ideal surfaces and so on. I'm not making any of those assumptions. Okay? And if I do the substitution of this into the other equation labeled 1, to substitute 2 into 1, and I'm just going to repeat the results from last time. I'm not going to go over it. You'll end up with Q1 is A1 times epsilon 1 times EB at T1 minus J1 because we can write E1 as epsilon 1 times EB at T1. Okay, so here that is the net emissive flux is a fraction of the emissive flux of an ideal body at the same temperature. So this is another equation. So if I rewrite this in a manner, and this is divided by 1 minus epsilon 1, of course. So I'm going to rewrite it in a manner as if the numerator is some potential difference, the denominator is some resistance. So Q1 is EB at T1 minus J1 by 1 minus epsilon 1, epsilon 1 A1. So this is thought of as a some potential difference divided by, now look at this, epsilon 1 is purely a surface characteristic. So this is called as a surface resistive resistance, surface resistance, okay, surface radiative resistance. So let me call this as equation 3. So far so good, right? This is where we stopped last time. Now I'm going to look at Q1 again, okay? So go back to the drawing board. Q1, which was A1 E1, E1 minus rho 1 G1, I can now rewrite it in the following manner. This is A1 times E1 minus 1 minus epsilon 1 G1 or alpha 1 G1 or Q1 is A1 times E1 plus epsilon 1 G1 minus G. I can now perform the substitution in terms of the radiosity. Okay? So in this case, I think this was right. This is going to be J1 minus G1, right? From here. So this is now A1 times J1 minus G1. And if you can use this expression here to come up with that same answer. Does everything look right? It doesn't seem to be the case. I'm missing something. Hang on. So this is rho 1 G1. That's right. So this is right. And if I come here, this is, the mistake was made here, I'm sorry. This is alpha 1, right? Sorry about that. So this is epsilon 1. Because alpha 1 is the same as epsilon 1. And that can be written as the following. So this is E1 minus, instead of alpha 1 I can write it in terms of rho 1. So alpha 1 is 1 minus rho 1. So this is 1 minus rho 1 G1. And then I can write it as E1 plus rho 1 G1 minus G1. Or this is A1 times J1 minus G1, and now we are talking. Okay? Okay. So please make a note. I had mistakenly written this as rho. This is supposed to be alpha 1. This step is not needed really. Instead of alpha 1, I am substituting 1 minus rho 1 because rho 1 is 1 minus alpha 1. And if I collect together E1 minus minus plus rho 1 G1, that is nothing but the radiosity that we had defined. Okay, so everything is good to go now. Alright, so we have Q1 is A1 J1 minus A1 G1. A1 J1 I can write it as 1 times, nothing is lost. Right, 1 times something is still the same thing. Look at A1 G1. A1 G1 is the net irradiative power that is falling on surface 1. Right, this is coming from all the surroundings that it has. We are looking at the 3 surface enclosure, so if I look at the net irradiative power on 1, it means that there is some portion of the radiation coming from 2, some portion of the radiation coming from 3. So I can say that the net irradiative power is equal to a fraction of the radiation leaving surface 1, surface 2, plus a fraction of the radiation that is leaving surface 3 and falling on surface 1. Is everybody on board with this particular step? Once again, what is this? This is A2 J2 is radiant energy leaving surface 2. Okay? Radiant rate leaving surface 2. If I multiply it by the fraction F21, this is nothing but the net amount of radiant energy that is leaving surface 2 and falling on surface 1. This entire term here, and maybe I should write it out. So if I look at this, F31 A3 J3 is equal to actually Q31, which is the net radiant rate leaving 3 as intercepted by 1. Because irradiation on 1 is coming from 2 and 3, whatever is the radiant energy leaving 2, whatever is the radiant energy leaving 3, a fraction of that is falling on surface 1. I add them all up, I'm going to be getting this guy. This is the crux of the problem. Okay, if this step is understood, problem is done. I want to see if there are any questions. That's equation 3. Save this, hang on to this creature. I'm just looking at the same equation but from a different standpoint. I'm bringing all these radiosities into play now. So if there are no questions, I'm going to do the substitution instead of A1, G1. Substitute these fractions and notice F21 times A2 is F12 times A1. Reciprocity. F31 times A3 is F13 times A1. Reciprocity. Okay? So I can say that A1, G1, and I'll just write it out. This guy is equal to F12 A1, F13 A1. So this is F12 A1 J2, F13 A1 J3. Take all of these fellows, throw them into the blender, and I rewrite Q1 again. I want to keep all of these. Alright, now Q1. Okay. Going back is A1, 1 times J1. Does not make any difference to any of our lives. Not yet. But F12 A1 J2. So far so good. This can get confusing because we're doing so many switches back and forth. But once you do it, you'll never forget it. It's very simple. Okay. What I'm doing is I'm looking at this expression, which is the same as equation 3. No changes have been made to it except that I'm looking at it from a different perspective. I'm introducing this radiosity creature. And I'm saying that, okay, this is the net irradiative power on surface 1 because of the fact that surface 1 does not see any of the radiation leaving itself. The net irradiative power on surface 1 is going to be whatever is the net radiative power from surface 2 falling on surface 1 plus the net radiative power leaving surface 3 intercepted by surface 1. Add those two up, write them in this manner where I invoke the reciprocity principle by saying F21A2 is F12A1. And we just have written that up somewhere there. Okay? Okay. Why did we write that creature 1? You see, that is really darn clever, isn't it? So now I do that substitution there, and you see what happens. This is now, and F11 is what? F11 is 0. Because we are assuming a flat surface. So 1 is F12 plus F13, do the substitution, so you see what is going to happen. This is now A1, F12, J1, A1, F13, J1, that's A1, J1 times this F12 plus F13, minus A1, F12, J2, A1, F13, J3. Or I'm going to collect like-minded terms. Okay, so from here I can say Q1 is A1, F12, J1 minus J2. You see that, right? A1, F12 is a common factor right here, right there. So that's J1 minus J2. Likewise, F13, A1, F13, A1 is a common factor. I take them out. This is all just mathematical gimmicks until this point. Everything is going to fall in place now. Now, this same equation can be rewritten as the following. Maybe I'll do it right there. Q1. That A1 F12, I'm just going to write it as a reciprocal of 1 by A1 F12 in the denominator. So this is J1 minus J2, 1 by A1 F12, okay? J1 minus J3 by 1 by A1 F13. This is also what? This is also reminiscent of a potential difference divided by a resistance. How is this tying in at that? Look at this. If I think of this equation 3, so this is equation 3, that's equation 4, those are our two equations. Equation 3, if I think of it as an electrical circuit, Q1 plays the role of current. The numerator is the potential difference or the voltage difference. The denominator is resistance. So if I label J1. These are the nodes. I can connect them by a resistor 1 minus epsilon 1 A1 epsilon 1. Q1 is flowing through. This is representative of equation 3. What's the equation 4 telling me? The total current is broken up into two branches. And so if I include that in that setup that I have, this is J3, this is J2, and those two resistances are going to be 1 by A1 F12, 1 by A1 F13. Does this make sense to everybody? This was from equation 3, this is now equation 4. But you see, I have a couple of other surfaces to take care of, and so here is what I can do. Surface 2 will have the same radiative network. Surface 3 will have the same radiative network. And I can join them all together now. And you can see that the last joining that I did between J2 and J3, it can be written as 1 by A2, F23, or if you like, 1 by A3, F32, whatever information you have. If you have F32, write it as A3, F32. And these guys will just be 1 minus epsilon 3, A3, epsilon 3, 1 minus epsilon 2, A2, epsilon 2, and so I have a complete resistive network for the radiation exchange between three surfaces or in a closed enclosure. I showed it only for one surface, but I can do the same thing for the other two surfaces as well. I can calculate Q2, which is going to enter through here. That's going to split into two branches, Kirchhoff's law applied at the node J2. Likewise, I'm going to have Q3. And whether the direction is from one to the other, that depends on the problem, of course. Okay? And so if I have a three-surface enclosure, this is the network. And that's about it. These resistances, which are 1 by A1, F12, they are geometric resistances. They're geometric radiative resistances because it's purely a function of geometry. Area here, F12 is a geometric character, so this is and you can do the same thing for four surface enclosures as well. Things get a little more trickier there because it is not necessary that the fractions F11, F22 be equal to 0. It is possible. If that takes place, then all of these will go to hell. But for things where the fractions Fii are 0, this always is going to hold true. For diffuse gray surfaces, opaque surfaces, where the fractions Fii are 0, you can always draw this radiative network for n number of surfaces. Okay? Now we are going to use this idea. We are going to go back to more angular origins. Let us just look at two surfaces. And we are going to prove something that we assumed at the beginning of the semester. Okay? With your permission, I'm going to slide this up. At the beginning of the semester, we had the following formula. If I had a surface, temperature Ts, And if I had large surroundings, temperature T, large surroundings does not necessarily mean that it is an ideal surface. Okay, it is possible that it need not be a large cavity, it could be an open surrounding. So in that situation, it's not an ideal surface, so I am not assuming this to be an ideal surface. We had assumed that the surrounding was large, the surface was diffuse and grey at the beginning of the semester. Which means that epsilon is equal to alpha for the surface. Epsilon s meaning surface. Okay. What was the formula that we had for the net radiative heat transfer from surface? Was sigma epsilon area Ts to the power 4 T surrounding to the power 4. I hope you remember this formula. We have used it multiple times in introductory problems. Okay, this was introduced at the beginning of the semester. Now let's prove this. Using our newfound knowledge of radiative resistance networks. So look at the same problem. Using networks. Small surface. Let me call that as surface 1. So its area is 1. Diffusion gray. Large surrounding. This is surface 2. Its temperature is T2. This is temperature T1. Temperature T2. I am not assuming anything about the emissivity of the surrounding. It can be whatever it wants to be. Area of this surrounding is A2. The only thing I'm going to assume is that A2 is much larger than A1. Okay, so we assume the following. Surface 1 is opaque plus diffuse plus gray. We also assume that A2 is much larger than A1. We are also assuming that F11 is 0. As you can see, this is a flat surface, so all of the radiation leaving surface 1 is going to go to surface 2, which means that F12 is equal to 1. Let us now draw the resistance network for this problem. This is now a two-surface problem. I have a large surrounding, I have this flat surface. Okay? So if I draw the resistance network, this is how I start. I always start with EB, which is the emissive power of an ideal body at the respective temperatures T2 and T1. Those are my first two nodes. Then I have two more nodes. They're going to be the radiosity of surface 1 and the radiosity of surface 2. J1, J2. Because I have two surfaces, I just need to have 1 and 2. If I have 3, I'll be having J1, J2, J3, EBT1, EBT2, and EBT3. Okay? Join all of them by the resistances. First resistance here, I'm going to call it as R1. Second resistance here. This is R2. This is purely a function of only the characteristics of surface 2 and surface 1. But in between I have R12 because this depends on F12. And F12 is dependent on the geometry of both A1 and A2. That's why it's called R12. Okay, so R1 is 1 minus epsilon 1 by epsilon 1 A1, as you can see from that figure that is drawn there. R R2 1 minus epsilon 2 A2 epsilon 2, and R12 is 1 by A1 F12. Now I want to see if there are any questions so far. Look at the number of surfaces. Fix the first two nodes. The primary nodes are EB, T1, T2 and T3. Secondary nodes are all these radiosities, J1, J2 and J3. And you join them together. If you're joining the emissive power to a radiosity, then you write that as a total resistance of that particular surface, because this is independent of what's going on in surface 2. This depends on both surface 1 and 2 because it depends on the fraction F12, which is a function of both the areas. Okay? Now, this is all Q, right? This is Q1. I'm assuming that there is a net radiative heat transfer from the surface to the surroundings. I don't know really if that is the truth, but let's assume that to be the situation. So Q1, I can make use of the idea that these are all resistances in series. So Q1 is the voltage at this node minus the voltage at that node divided by the net resistance. Okay, this is basic electrical circuits, series resistances. So this is EB, T1, EB and T2 divided by R1 plus R2 plus R12. I'm just going to write it out completely as 1 minus epsilon 1 A1, 1 by A1 F12, 1 minus epsilon 2 by A2 epsilon 2. Let's do the following. F12 is 1. So I'm just going to write it as 1. Then I'm going to take A1 as a common factor completely out. So this is EB T1, EB T2, numerator, divided by A1 is a common factor, so 1 by A1 is taken out. So this is 1 by A1. So that the first term is 1 minus epsilon 1 by epsilon 1. The second term was 1 by A1 F12, but F12 is 1. So that I just have 1 by A1 which I took as a common factor, so this is just 1. Third term is all of that multiplied by A1. Does this make sense to everybody? Once again, why did that F12 disappear? We just decided that, okay, F11 is 0, so according to the summation principle, F12 has to be equal to 1. A1 is taken as a common factor. Can somebody tell me what is that equal to? Approximately 0, because A1 is much smaller than A2, so the fraction A1 by A2 is approximately 0. Okay? Let's go. So if I now rewrite this expression, Q1 is EB at T1, Stefan-Boltzmann law. So this is going to be sigma T1 to the power 4, sigma T2 to the power 4 by 1 by A1. 1 minus epsilon 1 divided by epsilon 1 can be written as 1 by epsilon 1 minus epsilon 1 by epsilon 1 plus 1 and 0 is the last one. Does this make sense to everybody? I'm just selectively dividing through. Okay? Epsilon 1 by epsilon 1 is mostly 1. This is minus 1. This is plus 1. And so what do you know? Q1 is now